It's my pleasure to introduce our next speaker, Ms. Camila Belduque. She's an aeronautical engineer from Colombia. She's currently a mechanical and a manufacturing engineering grad student at Texas State University. She has experience in composites material, manufacturing processes, and characterization. Today, she's going to talk about magnetic and mechanical characterization of additive manufactured strontium ferrite polyamide 12 composites using twin screw and a single screw extrusion. Welcome, Camila.
Thank you very much, Roy. As he said, my name is Camila Belduque, and I did this project on the magnetic and mechanical properties of strontium ferrite and polyamide 12 composites, along with Ryan Robinson, Rijo Kala, Tanjina Ahmed, Adrian Medina, Jitendra Tati, and Wilhelm Ortiz. We are all from Texas State University. So this is our outline. After a brief introduction, we are going to describe our materials, which are strontium ferrite and Pa12, and how we manufacture filament composites via single screw and twin screw extrusion. In the results sections, we are going to compare the distribution of particles via scanning electron microscope and the magnetic properties measured with a vibrating sample magnetometer on both the filaments and the 3D printed samples deposited with and without an external magnetic field. We also tested the flexural behavior on the 3D printed samples according to ASTM D790. Okay, so to start, there are many advantages of the additive manufacturing processes, and they are all well known in the general manufacturing industry. There is a push to implement composite materials, mostly in fused filament fabrication processes, instead of the commonly used neat polymers such as PLA or ABS, because of the additional benefits and properties that the parts produced with these processes may require. And although these processes are currently bringing innovative solutions, it is important to understand how to obtain the raw materials for fused filament fabrication. So two methods are regularly used to produce filaments: extrusion and co-extrusion. Extrusion refers to a process in which one material is melted, and co-extrusion allows for more than one material to be mixed to create a composite or add different properties. Also, a cooling system is added at the end of the process to maintain the filament shape. Two types of machines are implemented for this: single screw extruders and twin screw extruders. The main parameters that govern the whole process are the screws, the temperature range, and the feeding rates. Different products can result from these methods, such as plastic films, pipes, tubing, and filaments. Some of the essential differences between the two are the temperature control. In the single screw, there are 3 zones, which are controlled from a software. Therefore, you only have 3 stages to melt and extrude your material, which leads to high shear and strain actions in the material. In the twin screw, there are 8 temperature zones controlled from the touch screen of the computerized controller and a degassing section. This design results in a very convenient heat transfer and therefore material with higher quality. Oops, we have to cut that part. Okay. Additionally, there are different screw designs that can be used in the twin screw, while in the single screw, this characteristic is limited. These differences make the twin screw process more expensive but faster. Types of screws, which can be single or 2 parallel, this also will determine the dispersion of the fillers and quality of the created parts and processing costs. Because it is possible to create all types of composite filaments with these instruments, researchers are exploring the area of magnetic materials for 3D printing applications and their mechanical properties with fillers such as neodymium and ferrites. Compared with neodymium, ferrites have a lower energy product and lower magnetic moment per volume density, but they are chemically stable and have a high corrosion resistance, which results in more durable parts. They also have a current point of about 470 degrees Celsius, which means that their working temperature is higher and can be added to polymers with a high melting point. Additionally, strontium ferrite has a lower processing and materials costs compared with neodymium and also nickel magnets. Magnets are also used in a variety of different industries and products. 3D printed magnets can provide a couple of unique advantages that most other production methods can compete with. Custom magnetic fields created during printing and scratch and shatter resistant magnets are two advantages that can be achieved by 3D printing that are not easily replicated by traditional methods. It is even more beneficial to use 3D printing in prototype and small production run capacities due to not needing custom tooling that is traditionally needed for custom magnetic parts. Okay, so we're going to use two types of materials in this study. They are nylon 12 powder from Evonik because it's high flowability and chemical stability. This indicates a good capacity to be mixed with other materials and provide a good adhesion. Additionally, it has a low moisture absorption compared to other polyamides. As filler, we're going to use strontium ferrite, OP71 from Dowa Electronics. It has a remanence of 151 EMU per centimeter cube, a coercivity value of 2,510 Orsted, and a density of 3.33 grams per centimeter cube, and a particle size of around 1.5 to 2.5 microns provided by the manufacturer. This material, the strontium ferrite, is a ceramic hard magnetic ferrite with a hexagonal structure and significant magnetic crystalline isotropy. Okay, so the first material being extruded is nylon 12 to find the conditions needed to adequately process the composite. So prior to processing, the nylon 12 was dried in a conventional oven at 60 degrees Celsius for 24 hours. And although very parameter was very carefully monitored, the material started swelling as shown on the right image. And different temperature ranges were tested to achieve a continuous extrusion, but the problem persisted. This elastic effect is known as die swell, and is caused by the high shearing action of the single screw to heat and melt the polymer. Consequently, it was not possible to add the strontium ferrite in this machine. And we can see in the image, the process need PA12. It has also some contamination and a rough surface, and the diameter is about 1.6 millimeters. Here we can see the parameters used in the twin screw extruder to manufacture both the knit PA12 and the composite. So this machine has two volumetric feeders. For knit PA12, we only use the main one, which has one screw. The temperature, feed rate, and screw speed varies according to the material. In this case, we decided to increase temperature a little bit above the melting point of the PA12 and also apply vacuum. And for the composite, we have to use both feeders. Again, we use the single screw to feed the matrix material, which is PA12, and when it reached the melting state, the magnetic particles are added using a mini twin feeder, which has two screws. We also increase the temperature when extruding the composite to reduce the pressure in the die. So in this picture, we can see that the difference between the two neat P12 filaments, the surface quality of the twin screw extrusion filament is clearly smoother, and there are no voids or contaminants due to the vacuum process. However, it has a smaller diameter, which we measured with a fila measure. And the bright parts that you can see in the image is only just like a reflection of the light in the lab at that time, but the quality is pretty good. Because it was not possible to manufacture a low void density nylon 12 filament with a single screw extruder, we decided just to make the composite filament with the twin screw extruder. In addition, we explored the effect of reprocessing the composite that we did. As research by others has shown that this approach improves the dispersion of the particles through the filament and also improves other properties. Therefore, after the first extrusion, the filament was cut into 3 to 5 millimeter pellets with a drill and reprocessed in the same twin screw extruder. Additionally, we followed the ASTM D792 to determine the density. We printed 5 by 5 by 1 centimeters cubed, where we found that they have a density of 1.38 grams per centimeter cube. These are the ACM analysis. So we performed this analysis on the two composites processed with the twin screw extruder, with the objective or understand the quality of dispersion of the fillers in the matrix. So we just cut 2 random parts of the filaments and coated them with a 2 nanometer layer of iridium with an image splitter cutter to improve the resolution. 3 sides of the cross section of each sample and their surface were observed. There is clearly a good adhesion between the matrix and the strontium ferrite, and although magnetic particles tend to attract each other, there is homogeneity in the particle dispersion of both filaments. No particle clusters were observed, and additionally, the images show a particle size ranging from 1 to about 6 microns, which can affect later the magnetic properties and the 3D printing process. To study the magnetic behavior, 2 samples of the strontium ferrite nylon 12 composites were 3D printed using a regular off-the-shelf 3D printer. One of the samples was printed in 0 field and one in a longitudinal print field of 5,500 Orsted, parallel to the bed of the 3D printer, as shown in the figure. For both samples, we used glue to improve the adhesion between the bed and the material. And for the lateral sample, the field was applied by 2 1-inch cube neodymium magnets, separated by a 1-inch aluminum spacer covered with a microscope glass. So on the right, we can see the axis of the printed samples displayed. And the vector N sub E defines the extrusion direction, and N sub C the normal of the print bed, and N sub P the third direction. And these are the results. So the first figure shows the magnetic hysteresis in the 3 main directions of the 5,500 Orsted sample. On the vertical axis, we can see MR over MS, which refers to the squareness ratio of the material. A well-defined square means that the domains controlling the direction of magnetization are well-oriented in the same direction and are hard to move. So this anisotropic effect is common in ferrites because of the hexagonal structure, and indicates a high coercivity in the material, which means that it is hard to demagnetize by either high temperatures or high magnetic fields. In this case, note that the squareness parallel to the field, represented by the blue curve, is largest when the field is applied parallel to the print field direction, which is N sub E. This indicates that the 3D printed material is anisotropic, and the print field induced a magnetic anisotropy in the composite by aligning the easy axis of the individual strontium ferrite particles along the print field direction. Here, the second curve shows the magnetic hysteresis for the zero Oersted printed samples for different directions of the applied magnetic field with respect to the sample's axis. Since the samples were printed with no magnetic field, the hysteresis curves show a much more isotropic behavior with hysteresis curves that are similar in all directions. And here we can see the hysteresis curves along the N sub E and N sub P axis of the filaments. The difference in coercivity between both curves is less than 0.3%. The magnetic moment dipole volume density of the reprocessed samples is approximately 11% larger than the original filament. The mass density of the reprocessed filament is 5% larger than the original filament. The uncertainty in both quantities depends on the determination of the sample's volumes. Here we use a caliper with a resolution of 0.01 millimeters and assuming a maximum error of 0.05 millimeters in all 3 dimensions. The uncertainty in the volume is estimated to be below 5%, concluding that the observed increase cannot be explained by errors in the determination of the sample volume. Additionally, the remanence of the strontium ferrite nylon 12 composites when the field is applied parallel to the radial direction is 31.54 EMU per centimeter cubed and 16.789 EMU per centimeter cubed when the field is applied parallel to the cylindrical axis. So, although the reprocessed filament has a higher remanence in both directions, which are 34 EMU per centimeter cubed and 18 EMU per centimeter cubed, these are not significant increase values. We can observe, however, that the remanence is always higher when the field is applied parallel to the radial direction. To determine the mechanical properties, we did flexural tests on the knit nylon 12 and the composites following the ASTM 790. So 5 samples of each material were 3D printed. This process was constantly monitored due to the rollers that pushed down the material getting obstructed. But the temperature was increased to 225 degrees for knit nylon 12 and to 235 for the composites. However, the same problem occurred for the latter at random stages of the printed process. This could be attributed to strontium ferrite being accumulated once the nylon 12 is melted again and blocking the nozzle, or decreasing the amount of material being extruded. It is recommended to use a 3D printed temperature of 260 degrees Celsius minimum. An example of some of the defects that we obtained during 3D printed can be seen on the images. Some of the lines of the layers in the final layer are smooth and the remaining layers seem to be incomplete, whereas on the other sample, the entire final layer is in good shape. Okay. After testing, some layers and lines were detached, mostly on the side of the surface and in the middle, but none of the samples broke. The flexural strength of the composite with a 40% loading level is 18% higher than that of neat nylon 12. Additionally, the flexural modulus was increased by 30%. As the mentioned loading level, it can be said that both the nylon 12 and the magnetic reinforcement have a good adhesion, which allows for better load transfer when a bending stress is applied. Therefore, the stiffness of nylon 12 is improved. And to conclude, we can say that 3 filaments were manufactured using twin screw extrusion, 1 neat nylon 12 and 2 strontium ferrite nylon 12 composites, one of which was reprocessed. The SEM analysis shows a good distribution of magnetic failure in nylon 12 for both filaments. We can also conclude that the 3D printed parameters used allowed to obtain the intended samples for both magnetic analysis and flexural tests. However, this process requires improvement to avoid the obstruction of the nozzle and obtain full density samples. Nozzle temperature changes and printing with an external field could be some of the solutions for this issue. Of our flexural tests show an 18 and 30% increase in flexural strength and flexural modulus, respectively. Different loading levels and other mechanical properties must be investigated to determine the optimum values at which this material could be offered as an actual industry solution. And additionally, the hysteresis curves of the filaments and 3D printed samples with and without an external field were measured. The easy axis of the filaments is found to be perpendicular to the cylindrical axis of the filaments. Similarly, the easy axis of the samples printed in zero field is perpendicular to the extrusion direction and shows a small anisotropy around the extrusion axis. The easy axis of the samples printed in a magnetic field is parallel to the field direction. Additionally, preliminary results on a single sample suggests that reprocessing the filament leads to a larger mass and higher magnetic dipole volume density. The authors of this paper are sincerely thankful for the support and advisement from Subhash Panta, Dean Kohini, and Juan Gomez from Texas State University. Their kindness helped make this work possible. This work was supported by the NSF through a grant under Award 17-26-970 and a research enhancement grant from Texas State University. Thank you very much.